In this video, I'd like to show you some ways to think and do physics with this gravitational interaction. Some of what you're going to see, what I'm going to describe to you, is very conceptual and very pictorial. So I'm going to have some diagrams and some ways to think about gravity just conceptually. But then as we go through, you're going to see that, in fact, actually, Newton's universal law of gravity is quantitative. It's a thing that you can use, for example, a calculator to do and to actually use the law to make predictions for how strong forces are in newtons. So I'll show you that. At some point, I'm going to show you where the acceleration due to gravity on the Earth comes from. I'm going to show you it in this section right here, kind of quickly, but I invite you to actually pull out your own calculator and work on it a little bit yourself. And then I'm going to discuss something interesting to talk about, like how could we tell how heavy is the moon? Like what's the weight force acting on the moon because of the Earth? So I'll indicate what you might need in order to calculate such a thing, because you could imagine maybe the moon is really heavy. Yeah. And then I'm going to indicate that even though the forces between really, really light mass things, the gravity forces, even when gravity forces are small, even when gravity forces are very small, they still have important consequences, even on the scale of galaxies. Okay, so yeah, so let's get started. So I'll go up to the top. So let's talk about some ways to think about the gravity interaction just with pictures. So what I'm going to do is I'm going to take two objects. Here is an object. It looks like a ball, and it's, let's call it A. And here's another object that looks like a cube, and just put it over here. So these two objects, because they have mass, we could say this has the mass called mass sub A, and this has the mass sub B. They could have the same mass. They could have very, very different masses. The thing about mass, though, is it's some number of kilograms, right? And it's never negative. There's no such thing as a negative mass, right? So that's not a physical thing. So the way that we diagram the gravitational interaction is the fact that these two objects, they are some distance apart, but because they have mass, gravity is going to cause them to be attracted towards each other with forces. So there's a force on object A by the mass of object B because of gravity. And there is an equal but opposite force on the object B by the object A because of the gravitational interaction. So just as an example, what if the force acting on A was 2 newtons? Then because of the gravitational interaction, there is also a force on the object B of 2 newtons that points in exactly the opposite direction. And attraction is the fact that the forces on the two objects point at the other object, right? So the force on A points at B and the force on B points at A. So the way I'm going to diagram the fact that when these two objects are closer to each other instead, so let's draw them slightly closer. So here is object A and object B. The force on A is going to be bigger, right? it's going to be attracted over towards B. Notice that even though I drew the arrow slashing through B, what's most important is there's a force on A towards the right. And now let's say that this force is now, let's say it's grown up to 16 newtons, right? 16. And because of Newton's third law and Newton's universal law of gravity, following Newton's third law, there's also force on B towards the left, also of 16 newtons. That's what I mean by saying that when two objects are closer, the interaction forces are stronger. Also, what if you bring in, or actually, what if A was actually a bigger piece of material? So let's say A is actually something similar to the Earth. And let's put object B close or somewhere. So here is object B. So these two objects are having a gravitational interaction, and object B is attracted towards the center of A with a big force, and object A is attracted towards the center of object B with an equally big force but pointed in the opposite direction, right? So if there's more material involved, then gravitational forces tend to be stronger. And if there's less material, gravity forces are weaker. When the two objects are closer to each other, right, so the distance between the two objects, that's meant to be a little d. When the distance between the two objects is smaller, then the forces are going to be bigger, right? So this is a situation where the distance was very much bigger and we had smaller forces. Okay, so this is the conceptual introduction to the way gravity works and the way that you can imagine drawing pictures of it and thinking with the pictures. Now I did put values of these forces, right? 16 newtons, 2 newtons, but diagrammatically, this right here is enough to get a pretty good picture of how gravity works. Okay, so let's move on to the quantitative, more careful description of gravity. So gravity is known as an inverse square law in the distance. But gravity is not an inverse square law in the mass. Instead, it's strictly that it's just proportional to the product of the masses. Product means multiply, right? That's meant to be a little times symbol, right? Product means multiply. And quantitatively, the way this thing goes is the gravitational forces. So the capital F stands for force, goes like, so this is not an equal sign, but it's a goes like. It's the product of the masses of the two objects. So the mass of one of the objects is called M1. The mass of the other object is called M2. But then it's inversely proportional to the square of the distance between the two objects, like this. So this is what's meant by inverse square law with the distance. You can see that the distance is down here squared. And then it's the product of the masses involved. You can see the product of the masses right here. Okay, so this right here is not an equal sign. The way that this quantitative rule gets drawn as an equal sign goes like the following. It's equal to a constant called capital G multiplied on the product of the masses divided by the distance between the objects squared. And this value G is very, very small. Even though it's given the capital letter G, G is actually 6.67 times 10 to the minus 11, right? It's very small. Newtons times meters squared divided by kilograms squared. And this is called Newton's universal gravitational constant. And it is very small. Whenever something is very, very small, when you talk about interactions like forces, what that means is weakness. Gravity is actually, in nature, the weakest interaction that nature has. But there's something really special about gravity because of the fact that gravity is strictly only ever attractive. Gravity is never repulsive. Interestingly, the other interactions in nature, like for example, magnet interactions or electrostatics interactions, those interactions can be either attractive or repulsive. So even though they're stronger, it turns out that you can actually kind of hide electricity and magnetism, whereas gravity, because it's strictly attractive, gravity never gets hidden. Okay, so let's move on. So this is a quantitative rule. You can see that this is actually an equation, right? It's an equation with a constant, and that constant has a bunch of units in it, right? So this is very much a physics equation that you can calculate with. All right. So here, gravity forces are significant when the mass involved, or one of the masses at least involved, is large. For example, say the mass of the Earth or the mass of the Sun. But gravity forces, even when very small, still have important consequences. Let's calculate, or let's sort of do the research of figuring out how to calculate what's known as the weight force of a 1 kilogram object, so this is the mass of an object, located at the surface of the Earth. So let's draw a picture. I'm going to draw a picture that's similar to this picture here. So here is the Earth. And the Earth has a really big mass. So the mass of the Earth is about 6 times 10 to the 24th kilograms. Wow, 6 times 10 to the 24th kilograms. That's huge, right? And we are putting a 1 kilogram object at the surface of the Earth. So that means that that little 1 kilogram object is somewhere up here. So the distance that this object is from the center of the Earth, right, is the distance between the two objects. You might wonder, like, if these two objects are touching, why isn't the distance 0? So up in this equation, actually, this distance, d, is between the centers. It's not between the outer surfaces, it's between the centers. So because this little 1 kilogram object is so small, the distance between the Earth and the little 1 kilogram object is essentially just the radius of the Earth. So we need to know what's the radius of the Earth. The radius of the Earth is about 6.4 times 10 to the 6 in meters, right? So that's the meter. 6.4 times 10 to the 6 meters. So when we go and we calculate this force, it's called the weight force, right? It's the weight force acting on the 1 kilogram object by the Earth, right? So that's what we're calculating. What is the weight of a 1 kilogram object, right? So the weight force is equal to G, right? That capital G, 6.67 times 10 to the minus 11 with all its SI units. And then we multiply by the mass of the Earth divided by the radius of the Earth squared, multiplying the mass of a 1 kilogram object. Right? Can you see that I just filled in Newton's universal law of gravity? So when you plug in these numbers, you see these are numbers that you can calculate with, right? And capital G is also a number, right, with a bunch of physical units. The result of this calculation is going to give newtons as the unit. And remember that we are calculating a weight force. What's interesting is you might put this in parallel with thinking about the old way that you calculated the weight force. The old way looked like this. You took the mass of the object that you cared about and you multiplied by the acceleration due to gravity where that mass was. Our mass is right here at 1 Earth radius from the center of the Earth, and the mass of that object is 1 kilogram. So what we would do, I'm going to switch the order of m and g and put g first, and then I'm going to multiply by the fact that it's a 1 kilogram object. And I wonder if you can see what I've done. If you look at everything sitting here, it's multiplying the 1 kilogram object's mass, which means that everything that sits inside of this bracket that I just drew is actually lowercase g, right? And this is the sense in which lowercase g is being predicted by Newton's universal law of gravity. So 9.8 meters per second squared, it's because capital G has its value, the mass of the Earth has its value, and the radius of the Earth has its value. And because of those three values, 9.8 meters per second squared is the acceleration due to gravity of the Earth, right? That's Earth data. If you wanted to know the acceleration due to gravity on the surface of the moon, you need to know the mass of the moon and the radius of the moon. And then can you see that you could calculate the acceleration due to gravity on the moon? Likewise, for anywhere else in the entire universe, you can calculate the acceleration due to gravity at the surface of the sun. You could calculate it at the surface of Saturn, right? Okay, so let's move on. Here's another example of thinking with Newton's universal law of gravity. Let's calculate, and I put it in quotes, or let's imagine what would go into calculating the weight of the moon. So let me draw a picture of what's going on between the moon and the Earth. So here is the Earth. And what the moon is doing is the moon is going around the Earth in what's referred to as an elliptical orbit. And that orbit kind of looks like this. So the moon is going around it. This little thing right here is the moon. And it's going around the Earth. And you can see that the moon sometimes is closer to the Earth than at other times, right? So this is when the moon is very far from the Earth, right? The distance between the Earth and the moon is large. And then this is when the distance between the Earth and the moon is small, right? And then this process just repeats. It just goes around and around and around like that. You take those little marks away. So if I wanted to know what is the force on the moon by the Earth, right? This is the force on the moon by Earth, right? Because of gravity, then what I need to know is how far away, what's the distance between the moon and the Earth? So maybe I would draw that as looking like this, for example. This is the distance between the moon and the Earth. And then the other two pieces of data that I would need, because I need to fill in this formula, is I need to know the mass of the Earth and the mass of the moon, right? And also you have to remember not the acceleration, the gravitational constant, Newton's universal gravitational constant, right? Which is the same value in any situation that you want to calculate gravity for. This capital G has only a single value. It never is different. That's the sense in which it's universal. Okay. So, gravity also has a lot to do with the formation and also, honestly, the destruction of stars and planets and solar systems and galaxies. If two galaxies run into each other, they can merge and become a single, bigger, more massive galaxy, right? And part of the reason why things run into each other is simply because maybe that's just the direction of how they were moving, right? So that was just their inertial path. But sometimes when two objects aren't necessarily aimed to hit each other, because of gravity, they can be attracted towards each other and end up running into each other, right? So here's the idea. Like, you might start off with a bunch of space dust, right? So this sort of cloud of space dust here, I'm just going to kind of weakly sort of draw a bunch of dust, and let's say it's headed this way, right? So that's some space dust that because of a star exploding or something like that. There is other space dust. Here is other space dust, right? That, for example, is headed this way. And these two big clouds of dust are actually attracted to each other gravitationally. So even though this might be the direction of motion of these two things, because of gravity, the blue cloud is attracted towards the orange cloud, right? So their paths ultimately lead to a situation where they swirl into each other. So the blue dust and the orange dust, there's kind of a coalescence. And this swirl of material, so this material is having what are called inelastic collisions with each other, right? So they crash into each other, break apart. Those are called inelastic collisions. And ultimately, this material coalesces down and gets, all of that matter gets sort of stuck to each other and can form, for example, a solar system or planets, right, within the solar system. So this is the idea, and it's the reason is because of gravity, right? Somewhat. It's also because things explode and spread out. But gravity also steers, the sort of evolution of large-scale structures in the universe. And gravity is really weak, so sometimes these processes, they take long periods of time to happen, right? And if you think about it, nothing is ever finished happening. It just keeps happening. Stuff keeps evolving, right? You may have heard that the Earth is continuously changing. It's not finished forming, right? We keep getting stuff from outer space, right? So Earth's not finished. Our solar system is not finished. Our galaxy's not finished. Our sun at some point is going to die and explode in some sense, and our solar system becomes parts in the future of other solar systems and galaxies.